Today I discuss one important topics related to matrix representation of a linear transformations. Okay, we know about that matrix representation of a linear transformation of a linear transformation. Matrix representation of a linear transformation. Understood? We write it now in this definition from. We start from definition. Okay. So let V be a finite dimensional. Let P be a finite dimensional vector space. Okay. Finite dimensional vector space. An order basis. An ordered basis. Okay. For V. An order basis for V is a basis, okay, for V endowed with a specific order, with a specific order. Understood? That is what that is an order basis for V. That is an ordered basis for V. Okay, an order basis for V is a finite sequence of is a finite sequence of, okay, linearly independent vectors, linearly independent vectors, okay, linearly independent vectors in V that generates V, that generates V, okay. Then an order basis for V is a finite sequence of linearly independent vectors in V that generates V. Okay, an order basis for V. An order basis for V is a finite sequence, okay, of linearly independent vectors in V that generates V. So understood this one? Too easy, okay. Some finite dimensional vector space, then a finite sequence of linearly independent vectors in V that generates V. Then we call these sets of vectors is an order basis for V. So we erase that portion and going to discussion some example related to that topics. Okay, so we start from an order basis and going to discussion of, okay, one related example. We write it here, example. Okay, in f cube, okay, beta equal to e1 e2 e3 can be considered an order basis, can be considered an ordered basis, okay, can be considered an order basis, and also comma equal to here e2 e1 e3, okay, is an order basis, is an ordered basis, okay, but beta not equal to gamma as a ordered basis, but beta not equal to gamma as a an ordered basis, okay. Why? Because here in beta this one is in a sequence e1 e2 e3 in this way, okay, and here in gamma, okay, here e2 e1 e3, that means this one is, that means this one are same set, okay, but in a not same order, okay, so not same sequence followed by this two, so we're not talk about, that means beta not equal to gamma, okay, in this way we talk about beta not equal to gamma here. Understood? Not a problem at all. So we're also going to discussion another one, that means in Fn, okay, in Fn what happened in Fn e1, okay, e1 e2 dot en, okay, the standard order basis, the standard order basis for Fn, okay, standard order basis. Understood? And obviously another example in this way in PNF, in PNF, okay, what happened in PNF 1 x square dot x to the power n, the standard order basis, okay, the standard order basis, okay. So now also, that means it is that portion and going to further discussion of one definition. I think all are understand this, okay. So now it is that and going to further discussion of something. Write it here another definition, okay. So we also discuss today order basis and gives one example related to that, and now we also discuss let beta equal to v1 v2 dot vn, okay, be an order basis, be an order basis for a finite dimensional vector space, for a finite dimensional vector space, okay, V. Then what happened for x belongs to V, okay, let a1 a2, let a1 a2 dot an be the unique scalar, be the unique scalars such that, okay, such that what x equal to here I equal to 1 to n ai ui, okay. Then what happened, then we define the coordinate vector of x, coordinate vector of x, okay, relative to beta, okay, and denoted by here x beta, okay, and obviously we write it this one denoted x beta and pi, obviously here x beta equal to x a1 a2 dot an. Understood? Then what happened? Then we also write it in this way. Okay, that means the coordinate vector of x relative to beta is this one. Okay, coordinate vector of x relative to beta is this one, a1 a2 an, in this way. Okay, now we also give some example related to that. Okay, we erase that portion and give some example. We write it here, example. Okay, here v equal to p2r and beta equal to, and let beta equal to 1x x square. Okay, with the standard order basis for, be the standard order basis for v. Okay, if fx equal to, if fx equal to 4 plus 6x difference 7x square, then what happened? Then if beta equal to, here 4 6 minus 7. Understood? This one is the coordinate vector of f with respect to beta. This one is the coordinate. Okay, coordinate vector of f with respect to beta. Okay, now we're also going to discussion another topics. We erase that portion and going to discussion another topics. Okay, so now we erase this. Suppose that v and w are finite dimensional vector spaces, are finite dimensional vector spaces. Okay, v and w are finite dimensional vector spaces with the order basis, okay, beta equal to, here v1 v2 dot vn. Okay, and gamma equal to, here w1 w2 dot wn and wm. Understood? Respectively. Then let t, here p to w be linear. Okay, then what happened? Then for ej, for ej1 less than equal to j less than equal to n, okay, there exists unit scalar, there exists unique scalar, there exists unique scalar aij belongs to f. Okay, here 1 less than equal to I less than equal to m, such that such that T of Vj equal to summation I equal to 1 to m Aij here Wi. Okay, for 1 less than equal to j less than equal to n. Understood? So in this way, V and W are finite dimensional vector space with order basis this one, and then we also discuss T of Vj equal to how we, that means how we write in this way. Then if we elaborate this one, then what happened? T of P1 equal to, here what happened? I equal to 1 to m, okay, ai1 wi. Okay, this one how we write in this way: a11 w1 a21 w2 dot 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 am1 wm. Understood? And here in this way, T of v3 equal to what? I equal to 1 to m a I3 wi equal to a of 1 3 w1, here 2 3 w2, here 3 3 w3 plus dot 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 here m3 wm. Understood? Okay, now we're also going to discussion of some definition. We erase that portion and going to discussion some definition. Okay, okay, now we write some definition here. The n cross n matrix A, okay, the n cross n matrix A defined by what? Defined by aij equal to aij. Okay, the matrix representation of T in order basis beta and gamma. Okay, the matrix representation of T in the order basis okay, beta and gamma and write okay, a equal to T here beta gamma. Okay, then what we write? That means if V equal to W, okay, if V equal to W and beta equal to gamma then we write okay, A equal to T beta. Understood? And another way we also defined in this way, okay, if u and v if u v to w, okay, if u v to w, okay, is a linear transformation such that u of beta gamma with respect to beta gamma, okay, u equal to here T beta, that means with respect to beta gamma t, this one happened, and obviously u be a linear transformation. Then what happened? Then u equal to t. Understood? So now we give some example. That means we also write this one, the matrix representation of t, okay, in the order basis beta and gamma. Now we give example of that topics. Okay, we erase that portion and going to further discussion of that. Here we write example. Okay, here we write example. Let t r squared to r cube be the linear transformation, be the linear transformation defined by, okay, t of a1 a2 equal to what? Equal to a1 plus 3a2, here 0, here 2a1 difference 4a2. Understood? Now let beta and gamma be standard basis for, be the standard basis for, okay, r square and r cube respectively. Okay, then what happened? Then beta equal to what? Here 1 0, here 0 1, and gamma equal to what? Here 1 0 0, here 0 1 0, here 0 0 1. Okay, then what happened is here we write it now. Now t of 1 0 equal to what? Equal to 1 0 2, equal to what? 1 e1, 0 e2, and 2 e3. Okay, and t of 0 1 equal to, t of 0 1 equal to here 3 0 minus 4. Okay, here 3 e1 plus 0 e2, here minus 4 e3. Okay, hence what happened? Hence t beta gamma equal to what? Equal to 1 0 2 and 3 0 minus 4. Okay, 1 0 2 and 3 0 minus 4. Okay, then if we change, that means in this way we also represent some matrix. If we change this order of, that means if we change here beta to gamma dash, then e2 e1 e3, then what happens? Okay, if we change, if we change in this way, then what happened? We write it t of beta gamma dash. Okay, then this 0 is first, then 1, then 2, and here 0 is first, and 3 and minus 4. Understood? Okay, then in this way we also change, that means in order of, in orders we change this order of this basis vectors, then obviously we get different matrices. Okay, so order matrix plays important role. That means just basis is not required here. Order basis plays important role in matrix representation. That means order are important. That means sequentially this pattern is important. Okay. So we also discuss another definition related to that topic. Okay. So we erase that portion and going to another example. Going to discuss another example. Okay. So we write it now. Let T P3R2 P2R. Okay, P3R2 P2R be the linear transformation. Be the linear transformation. Okay, defined by T of fx equal to f dash x. Okay, and let beta and gamma be the standard order basis. Be the standard order basis for P3R and P2R. P3R and P2R respectively. Okay. Then what happened? Then T1 equal to 0 and this one equal to 0 1 0x 0x square, and here T of x equal to what? 1 equal to 1 1 0x and 0x square, and T of x square equal to what? Here 2x equal to 0 1 2x 0x square. Okay, then what happened? T with respect to this beta gamma. Okay, then we write it in this way. Okay, beta gamma, that means T is far from P3R. Okay, so another one is required. We erase that portion. Okay, another one is required. This one is Tx cube. Tx cube equal to 3x square. That means 0 1 here 0x here 3x square here 0x cube. Not 0x cube is not now here because this one is P2R. So T is represented. That means how this T is represented? T of beta gamma equal to what? Equal to, we write it in this way, 0 0 0 1 0 0 0 2 0 0 0 3. Okay, in this way we represented this 0 0 0 1 0 0 0 2 0 0 0 3. Okay, in this way we represented this one, this T. So we also discuss, that means how one linear operator represent, that means matrix representation of linear operator, how this one is formed. We also discuss by this example. Okay, I think all are understand these portions. I think all are, that means evaluate this linear transform matrix representation of linear transformation. Okay, so if you want to get this type of videos, please subscribe my channel, and if you want to give like, please click on like options, and if you have any questions, comments, suggestions, write it in comment box. So I think all understand these portions. If any doubt, please, that means write it in comment box, and obviously see these videos from first to last, and obviously understand these topics. This one is better for your study. Okay, so today I stop here, and please subscribe my channel. Thank you.